That's an image we produce with our technology, and these images are produced by many other groups, not only by us. So what you have now, axial, you have a 3 micron, and in vivo. To collect this image, you don't need more than millisecond now. With the modern technology, you can collect this in milliseconds. You even don't need to dilate the eye. It's totally non-invasive. And ophthalmologists, now they know what to do with all these layers. All those acronyms, they know what they mean. And generally, disease comes here in the central part of the eye. We call this central part of the eye fovea. The photoreceptors are somewhere here. And bad things happen in those cases which we refer to age-related macular degeneration. This is a degeneration of the macula. People with glaucoma will suffer from this layer. You see this layer here? This is called nerve fiber layer. This is the layer which collects the electrical pulses and sends the pulses towards the brain. So due to pressure in the eye, the vitreous is here, above. The vitreous is here. Okay. So due to pressure in the eye, this nerve fiber layer gets thinner. And that shows the onset of glaucoma. In glaucoma, that's where the sufferance takes place, in the optic nerve layer. This layer here becomes thinner. So now ophthalmologists who are not engineers, not technicians, they regularly measure the thickness here with micron resolution. So you realize clinicians now went into that specialty instantly, patient by patient. They could tell you with accuracy of micron how thick is that layer. As well as you can see many other layers, and they all mean something here. Okay. The previous image has identified only what we call here retinal pigment epithelium, which was this one. That's the only one which we could see somewhere here. Okay. Retinal pigment epithelium. But there was no way to separate them there, because the axial resolution was the first image. While here, with better optical sources which have a coherence length of 3 microns, the length of that wave plane started with, which is only a couple of microns, we can separate these on real cases, one human eye in vivo. And I'll show you more of such images. So the power to the eye is less than the safety threshold, which is about 0.75, slightly more. All commercial systems will operate at 0.75 milliwatts. Wavelength is somewhere in infrared, so the patient cannot see that, so it's not always safe, but it doesn't stimulate the eye, because you cannot see it under 40 nanometers. Which is the longest wave the eye can see? The longest wave. Close to 670 already person. So 840 you can see. Cornea, the same. You have with high resolution. The eye lens is here. So you see this is a cross section. So this scan. This is depth. This is lateral. So you can see the accommodation, and you can study the accommodation. If you modify the light into the room when you collect such an image, what do you expect to see? So if I increase the light into the room, what do you expect to see? This is the iris. Yes. So if the light goes, if you turn on the light, the iris will try to restrict the light going to the retina. So you'll see this in real time moving. If you go into the dark, this will retract. You can see that in real time. It's not like in CT where you have to wait for the image to be calculated. So it's real time. It's real time instrument. Cornea is larger magnification. So cornea is about half micron. You take half micron and multiply by the index of refraction of tissue, which is about 1.4. You can obtain something like 0.76 something millimeter. So there you see a layer of tissue of 0.7 millimeter in depth, okay, which is resolved with, I think this image had about 7 micron axial resolution. So you see the bone layer here, you see clearly the endothelium, and the lateral here you have seen it. Good. So if you wanted to go more into the technicalities of the OCT, you should go to this paper in Journal of Microscopy where I explain the technology. So far, I only explained the technology which is practically less and less used. And all the 3 types of technology are expressed in this review paper, and this is easy to read with very little mass. So you go to Journal of Microscopy, and you should find it. It's open access, so you can download it. Now, the time domain is something which we also teach to our second year physics students, because that's the basic of OCT, and that's the way the first OCT has been produced using time domain. However, time domain is still used in microscopy OCT. It's less and less used in medical applications, and you'll see immediately why. So now I'm going to explain the other 2 types of OCT. The modern OCT. The OCT you are going to see in cardiovascular is one which uses tunable laser, basically. So now it's a laser which is tuned and fast. Okay. So let me take you quick through those 3 types. So again, the Michelson interferometer is there because OCT is interfering, so you have to superpose light coming from the tissue with light from a local reflector. So that is still there. Okay. What you also need is to place here a pinhole, like in confocal microscopy, to avoid, to eliminate the off-axis rays. Okay. And you need a microscope frame and the broadband source. So that all these were the ingredients of the time domain I have just finished. Fine. So that was the time domain. So what was the way to select in depth? This length is equal to this, so I'll see fringe pattern from here. If I wanted a fringe pattern from here, I have to move this up, and now this length will be matched by this length. If I wanted to see here, this length, I have to move the mirror to somewhere. So by moving that mirror, you practically select the depths in the tissue where you create interference from, based on selecting the optical path difference. And as long as the OPD, optical path difference, is less than that 5 micron, 10 micron, we call it coherence length, which is the wave train length, okay? You get C. Everything else doesn't produce interference. Now, the second type, which is practically the most used type, now look at the difference. That's the only difference, not much. That's the only thing you have to change, and you obtain the modern technology, which not every commercial system in the world now uses this, but the tendency is for the next, let's say, 5 years, we will see more and more of this principle. So instead of a broadband laser, you use a laser. Now the laser will be practically monochromatic, a well-defined emission, but you tune it. And to achieve again the axial resolution, you have to go into that boundaries. I told you that boundaries give you many colors, and those many colors determine the length of the wavelength. The more colors you put, the shorter the wavelength. That's the idea. So a laser, which has to be a laser, but is tuned within that large boundaries, 50, 60 nanometers. And that's the only thing you do. And that is called the swept source because you sweep. It's like a tunable laser which you should tune fast. A better term for tuning fast is sweeping. The other principle is this one, which is practically dominating in the commercial world now. This is the time. Broadband source back. But do you see spectrum. So this type, and that is the tuning laser, is practically the same thing. And I will explain immediately why. So these are the two modern types of OCT. One using the camera, and a lot of commercial systems use this principle. And this one is using a swept laser. So you see here the interferometer. So light from the broadband source goes to the reference, comes back. Goes to the sample, comes back. Light from the laser goes to the sample, comes back. Light from this tunable laser goes to the reference pass and goes to this tank. So a camera-based system or a swept source system. So this will be called an SSOCT. This will be called camera-based. Sometimes this is used as a, you see, a Fourier domain. Well, all of ophthalmologists practically refer to this principle as a spectral domain OCT. Why? Because in most cases we operate with the spectrum. So this is a spectrometer. How do you build the spectrometer? So this is the interferometer output. You put it on a diffraction grating. The diffraction grating will diffract different wavelengths, different angles. And with a lens, you collect different colors on the camera here. So on these pixels you have the red, on these pixels you have the blue. So practically here we display the spectrum and the interferometer output. You may say, what is the spectrum here? In fact, this one is exactly this one. Why? Because in this spectrum you practically sweep, you move that Dirac delta function, that very sharp wavelength, you move it in the spectrum. And what you collect here in time is practically the spectrum. So this signal which you collect here from the camera is practically the same electrical signal here. So this signal is exactly equivalent. That's why they may be seen so different, but in fact the physics is the same, because the electrical signal here and here is the same. Let me tell you more about this. The spectrum coming from an interferometer, or the optical pass difference, is 3 lengths of the waveframe. If you do that math, I'm not going to spend time on that. Okay. We'll have this number of peaks. Okay. If you stop one of the beams, the spectrum will be like that, a Gaussian. It will be white in the bandwidth of that broadband source. If you now leave both beams, you will have maxima and minima. This is the fringe pattern. Now, this is wavelengths. I can see the spectrum with a camera, with a spectrometer. But I can also obtain the same thing if I create a slit in the paper and I move the slit along. So if I have a slit which I move it along, I will go up, down, up, down, up, down, up, down, up, down. So I can read the spectrum with a tunable laser. So look, let's tune it. If I tune it in time, I obtain this. Let's now refer to the signal of interference coming from a depth which is placed at a deeper depth in the tissue. Let's say that that scattering center is at 8 values of the waveframe length. 8 values of the wave. In that case, the spectrum has all these peaks. With the spectrometer, the camera will give me in time, this time, signal. With a tunable laser, I could re-obtain the same thing in time. So practically both light cameras in the spectrometers and the photodetector in the swept source give me in time the same thing. Did you get this? You want me to tell you more about it? What is hard to understand? Everything. Do you have that idea about an optical spectrum? What is that, an optical spectrum? You heard about the rainbow. What is the rainbow? So every OCT, modern OCT, will have a prism or a diffraction rating spreading the wavelengths over a line cover. So they will read, the camera has a number of pixels, 1,000 pixels, the lens. So this is color, like wavelengths. And this is the spectrum and the interferometer hour. Don't worry, even our physicists have difficulties with this. And that's why we teach them the time domain first. This is slightly more difficult to comprehend. But you have more in that review paper, so I invite you to read more there. Good. So let's say that you now know a little bit more about these three types of OCT. I have half hour more. So your tissue is made from many scattering centers in depth. So if I did an A scan, I should practically obtain a peak here, a peak here, a peak here, and so on. So all these scattering centers will return light. So the spectrum for this depth, after interference with this, will be modulated by a number of peaks. This is deeper. So that corresponds to a longer, minus this, to a longer OPD. So there will be more peaks in the spectrum. So along this coordinate, I have the spectrum. You see? For this scattering center, it is even deeper. I have more modulation. So all these three signals are practically superposed. The spectrum, because the light coming from here, it comes at the same time. So you have this spectrum superposed. So practically what the camera will see, what the photodetector will give you when I shift that delta D wavelength, we'll see a superposition of these three. So that's how the spectrum will look like. So for a sample made from three scattering centers, from three layers, you will have three modulation all superposed. So now, if you take this temporal signal and you do a Fourier transformation, you also have to learn more about what the Fourier transformation does, which is not part of my lecture. You do a Fourier transformation, that means that you identify the components now in the spectrum, which is in time of the signal. So now you have a peak for this, a peak for this, and a peak for this. So you get 3 peaks. Practically these 3 peaks will practically correspond to depth 1, depth 2, depth 3. So you obtain that A scan. More on the difference between these principles is, as I already explained, the time domain works around optical path difference 0. You obtain a single signal only from that depth where the scattering center is at a length which matches the length from the reference mirror to this optical path difference equals 0. While the spectral domain and Fourier domain, those two principles, which are most used today, practically all those layers produce that modulation in spectrum at once. So that's why the spectral Fourier domain are more used. You don't need to mechanically scan the mirror. Your mirror is fixed in this. And the spectrum takes all the difficulties. That spectrum has already the modulation of all the interference events. For all the scattering centers in depths, you had for each a modulation, all that modulation complex, assembly of modulations for all, let's say, 100 scattering centers. Each one in depths will have determined its own modulation. So it's like you have a spectrum superposed from 100 modulations. If this layer had the more light return, its modulation will be stronger, but the number of peaks will be connected to the distance up to the B splitter. The other depths, its intensity will be given by how much come from that center. But the modulation will be given by at what distance is that depth from the B splitter. So by doing the FFT, now you obtain the number of peaks. And by you obtaining the number of peaks, you obtain the A scans. Okay, so that you should know about this on your own. That is a comparison. So let's go back to this physics now, because it's better for you to understand and do a lot. So again, to this principle of superposing wave trains. So remember, the wave train is 400, 500 terahertz, it's fast oscillating, and if you work out which is the length here, this is wavelengths, let's say, and this is the wave trains, which is as long as determined by the inverse of the bandwidth. So if you delay it, this superposition will get less and less. So you realize now that different centers in the tissue will push this wave train to be. So this is, let's say, from one scattering center. A scattering center which is deeper will have this wave train here. So here and here and here and here. So you see the amount of overlap will get lower and lower. And if you use the swap source principle, practically the wave train here is like a time domain. Its length is inverse proportional with the lines. And now you have a laser. A laser will have a line width of about, let's say, 10, 20 kilometers in comparison with the broadband source here, which is 100 nanometers. So instead of 100 nanometers, if you put in that formula a couple of kilometers, this coherence length, the wave train length, becomes centimeter. Okay? So that shows the limitation of the method. That here, now the wave trains, which before was used to give you the resolution, in the swap source technology, this wave train is practically giving you the maximum penetration depth. Not penetration depth or you get nothing from the tissue. Maximum, or you can still produce interference, even if you didn't have any attenuation. So that's the physics behind. Practically, you should see this coherence length playing its role with these two technologies. In the time domain, this determines the axial resolution. In the swap source domain, this determines how long can I create this delay for these two wave trains to still superpose. So here, the condition is that you can go as deep as the coherence length of the laser, but use a laser. Optical sources for OCT, I'll get you quick through this. There are all sorts of sources. They are derived like semiconductor lasers. You equip them with a fiber, so you have in one point spatially coherent, but they emit in a large boundaries. And these are called superluminescent diodes. You put several together. The titanium sapphire laser is also broadband and has been used in OCT. And the most modern one is this, coming from these companies, which they use something which is not going to be done by any of the 3 ELI centers. No, none of the centers will do the supercontinuum. But it's another type of lasers. If you want to know about lasers, you should also read about supercontinuum. Supercontinuum is you take a second, 30-second pulse, you send it to a nonlinear fiber, and you obtain this all sorts of nonlinear phenomena in fiber and generate a supercontinuum of wavelengths. This is ideally suited for OCT, for high resolution OCT. And that's the source from NKT Denmark. And these are two technologies which are relatively new. So OCT first invented 1991, the fiber-based supercontinuum 1999. So these are two physics inventions which coexist and determine the growth of the technology. You can put together fiber lasers, and here I'm showing you results. One, what exactly we should do OCT? The eye is the main tissue for the OCT. So that's the absorption of water. So what do we see here? We see that in this region, close to the spectrum for the eye sensitive, we have that's why water is so important for imaging the retina. And we know from optics of the tissues that the longer the wavelengths, less is the scatter. Now, so we would like to use longer wavelengths to have less scattering and better penetration. And that is used today in imaging skin. Why? Because in skin you can go up to this region because there is little water. However, if you wanted to see the retina, which is at the end of 4 centimeter photons spending time in water, you will encounter this absorption. So now the modern OCT technology for the eye has found a trade-off. Longer wavelengths for lower scattering to penetrate more in the retina, and to have less absorption from the water. So that is one region which is called 1060 nanometer region, and that's what the majority of OCT system for the eye will be soon. So here we build such a source, putting two sources together, and we obtain that coherence length, that wave train of only 7 microns. So if you vary the optical path difference in the microns on interferometer, if you went away from OPT 0, you got here maximum, and nothing if you are above 7 microns. So that shows that with such a source you can separate layers in the retina, separated by more than 7 microns. And here is a demonstration of the value of using longer wavelengths. So that's an image of the retina, and the most commercial systems will have these wavelengths. Okay. And most commercial systems will use cameras here. The camera based, what they call spectral, so that's depth, that's lateral. Okay. So this is called choroid. And ophthalmologists manifest a lot of interest to see deeper and deeper in the choroid. Look, by changing the wavelengths, look how much more we can see. See, I can see much more. Compared to this is called choroid. So by increasing the wavelengths, only by increasing from here to here, by moving from these wavelengths to these wavelengths, the scattering is less. So now we have sufficient, even if there is some more attenuation, we can still see better. And now the systems.
Excuse me.
Yeah.
This condition is for wavelengths.
I didn't get the question.
This is optimum conditions for the wavelengths.
What do you call by optimum?
Optimum.
What do you call by optimum? They are both optimized OCT systems to work. The laser safety, that's also true, that the safety power is different. That wavelength is 0.75 milliwatts. Here we can apply up to 1.7 milliwatts. And that's what has been applied here. So it's a little bit more power. Okay? But it's still under the safety. If that is what you meant, both are OCT systems in our lab, and these are images produced by many groups, similar. Okay? But that shows that by changing wavelengths you can penetrate more. Take that message. Good. Now, I told you a lot about broadband sources. I should also tell you about how we build a tunable laser. So you build a ring laser, place here a semiconductor amplifier, the filter. So this type of source didn't exist before 2000. It was the OCT community to create these fantastic sources, which now go to tuning. If you look at the technology of tuning lasers, you will find only kilohertz range. Not kilohertz, hertz, different hertz. Tune a laser. Now this type of laser will go to over several megahertz. So you can do an A scan 10 megahertz. Look at time domain OCT. You have to move the mirror to produce an A scan. How fast can you move it? You can use a turbine and indeed you can do it kilohertz. But is this principle, or nothing is in the OCT is moving? Of course, that is mechanical, that tunable. It's a little bit, very little mirror there. cell sweat sources. Here we put together, this is obtained with a 1060 nanometer in skin. So what do we see here? From here to here we have something like 0.81 millimeter in depth. Okay? That's called stratum corneum, so that's an image from the finger. Okay? So in the fingertip we have this stratum corneum, and what do you see here? What do you think you see here? In between the stratum corneum and epidermis. What do you think are those? If you put your finger in my system, in all your fingers you'll see this. So from here to here we have 0.8 millimeters. So we can resolve scattering centers in that, but this is 5 micron axial range. These are helicoidal ducts. They take the water from the body and expel it out. These are the sweat ducts. So if you increase the temperature in this room, this will inflate to allow more water being expelled. Okay. You obtain such a volume in less than half second with modern technology. There is also a trend in image presentation towards unphased. There are conferences on called, if you remember the unphased, the C-scan, producing a C-scan image, a constant depth image. And there are now more and more conferences on unphased technology. And these are grouped now with a trend in showing vessels. And to display vessels in body, we used, how is it called, the technology to display vessels? In the medical.
Doppler? Doppler?
Doppler ultrasonic.
Okay, fine. Yeah, but there is a vessel which is quite well spread.
You mean in tomography? Tomography?
Angiography.
Angiography, sorry.
There are two drugs which are injected in the body, and we look at fluorescence. One is ICG, green, and the other one fluorescent. So they are injected, and you use fluorescence of that emitted wavelength drug. The drug is emitting fluorescence. You look at fluorescence and you see the vessels. But that is, let's say, invasive because you have to inject the dye. Now, using OCT, you don't need to inject. You can see the vessels by simply. Because OCT is based on interference. I.e., you do interference at two beams. It's like heterodye. You superpose two waves. It's like beating. So if there is anything moving, that bit will create a Doppler shift. So if you now look at that bit, you can identify that signal came from a vessel, from a flow scattering center which was moving. So in this way you can distinguish between the vessels or cells are moving and the rest of the tissue which are the tissue is stationary, it's not moving. And you can separate that. And you don't need now an injection to make the difference. You don't need to inject. That's why the technology is so great. You don't need to inject. So that was one of the first systems based on time domain to produce unphased images, and it was a collaboration with colleagues in Europe in Filmering. So what you see here, you see cross sections from different diseases. See the diseases here? This is the cross section, and modern technology still produces these images of the retina. So that is depth lateral. So for the IP detachment, look at the previous images were from healthy eyes, which I have shown you. Now these are images from diseased eyes. Look at the image. Look what happens here in the retina. That's devastating for the eye. There is fluid here. Especially here, in the case of CSR, central cerebral retinopathy. But if you do an unphased image of that, look at how images look. They look very different, that they can provide this association of patterns. There is a lot of work in deep learning, in machine learning, in identifying disease being made by machines. the machines will combine soon this view with this view and do the diagnosis, diagnose without needing us, without needing ophthalmologists. Press a button and they will tell you, you have this. So associations of patterns in B-scan, C-scan would help them. Idiopathic polypoidal choroidal vasculopathy. That's the case here. Look how devastating is that for the eye. The scanning laser ophthalmoscopy will show you this is the fundus of the eye. Look here, this is an unfaced OCT image. And the cross sections at those two areas. So obviously here penetrated more. Look what happens in the eye. Do you see that this patient still sees? Yes, it does. But sees only a little bit because the fovea is so distorted here. There is a lot going on here. So that's the concept of fluorescence. Okay, I have 7 more minutes. Let me take you to the modern technology. In the modern technology, we now operate faster on the scans, and we build the volume of the scans, and then cut the volume and produce an unfaced image. That's the way the modern technology is produced. Time domain could produce it in real time, but it was slow, and it's not so sensitive as the spectral domain. As I already told you, all those scattering centers produce all those modulations, many modulations in depth in one signal. So that's a big advantage. It's not like in time domain where for each depth you have to put a mirror at that position. If you wanted another depth, you have to move the mirror. Here, you don't move anything, and the spectrum will give you all the modulations for all depths. That's why the request of using the camera or using a tunable laser to cover. However, because they are based on scanning the spectrum, it's like you go along the depths, you go like with A scans. So you need to assemble all the A scans for all the pixels in the transversal section. For all these pixels, you have to build these A scans. You put them together, and then you have to come with a software procedure to do the cut and show the image in the unfaced view. So I would invite you to read from our webpage a new method which is called master slave, which is explained here. And that will be the end of my presentation. So that's novel technology coming here. So the two modern technologies I presented, they are based on investigating the spectrum. And the modulation is called channel spectrum. So that's the modulation, let's say, for a given optical path difference. You do an FFT of that, and that is A scan. So that will be along the depths an A scan, amplitude along the depths, that's the A scan. So you obtain that with FFT. In our technology, we have a processor for each depth. For each depth there is a processor. We produce that now in real time. Instead of doing a FFT, we have a processor. And that has several advantages, and that's explained here. So the conventional technology, as I already explained, used an interferometer, that was the Michelson, photodetector or a spectrometer, produced the spectrum. We generated the FFT of the spectrum and produced the A scan. We don't do this anymore. That has all sorts of disadvantages, which I explained in our papers if you have time to read. So what we do now, we conserve the modulation, which we put it in the storage, and we compare that stored pattern of channel spectrum with whatever comes from the tissue. And if a similar modulation is here, we say, yes, that modulation is already in the signal, so we identify that there is a scattering center producing the same modulation as that for the depths we are after. And if you do the comparison with 1,000 such spectra stored, you have 1,000 points in real time. And it's called master slave because this is the slave interferometer, and that will be the result of the master interferometer. Okay. And I have a couple of minutes to close, so I'll go to the end. And I'll send you a PDF with This is a list of topics which are from Web of Science where they've been touched by OCT. So you see here ophthalmology, cardiovascular, public environmental, occupational health, microbiology. So what we did in Cantwell, we looked at all this, and now recently we look at surgery and robotics. There is an interest in mounting OCT instrumentation and robotics, robots being used in surgical interventions. If you wanted to know more, you can Google OCT news. You write OCT news, and you can subscribe to receive regular news. Each week, one of the inventors of OCT at MIT sends data on what happens in the OCT field. OCT is used in all sorts of medical disciplines, branches. To hear more about what we do in Kent, if you Google Virtual Center of Biomedical Optics, you come to us, you'll see applications in the retina, cornea, larynx, skin, basal cell carcinoma, villi, tympanic membrane, neuronal tissue. We looked at embryos of Drosophila, dental constructs, which we do a lot with University of Timișoara, Romania, where I go tomorrow to, art conservation, and adaptive optics to improve the astigmatism and other problems of the eye. And so if you copy this link, that will take you directly to tinyurl.com/K26MDev will take you to our webpage. So tiny URLs are created automatically. So what you have to write is .com